Hello everyone, my name is Xiatao Sun, and today I'll be presenting about my project that is on imitation learning for autonomous quadrotor flight. My advisor is Professor Vijay Kumar. How do I- So here is the outline of my today's presentation. I'll first introduce the topic by talking about the motivations, contributions, and challenges of this project. Then I'll go through the methodology that I use on exploring this project. Next, I'll share some experiments and results, and finally, I'll make the conclusion and talk about the future work after this project. So to introduce the project, I'll first talk about the motivation of it. Traditionally, we usually use optimization-based approach for quadrotor trajectory planning, which typically consists of a front end, a pass-through chain, and a back end for optimizing the trajectory. However, as we incorporate more and more optimization constraint onto this type of traditional planners, the computational costs become more and more expensive. This issue is further amplified by the fact that the traditional planner typically decouple the planning process into several different sub-modules for things like converting the depth image to point cloud or generating the safety corridor for planning, etc., which generate additional communication costs, which then further amplify the total computational overhead. And therefore, we need a way to reduce the computational cost of traditional optimization-based planner. And you can see that on the bottom of the slide is a table comparing Agile Autonomy, which is a learning-based planner, with two traditional optimization-based planner. And although Agile Autonomy is not a fully end-to-end learning-based planner, it is still able to outperform the traditional optimization-based planner in terms of the total planning time it used. And therefore, it brings us to one possible solution for addressing the problem of increasing computational overhead of traditional planner, which is we can use certain knowledge distillation techniques to learn a low-cost neural network-based policy that can approximate behavior of a given expert planner. And imitation learning is one of these techniques that can help us to achieve this knowledge distillation. However, before we apply imitation learning to this task, we need to first have a framework that can effectively replicate the behavior of any given expert and being able to learn quadrotor trajectory planning properly while also having the compatibility with ROS. Moreover, beside the traditional optimization-based approaches that I just talked about, most prior work in quadrotor trajectory planning that focusing on using a learning-based approach, mostly exploring with reinforcement learning, whereas on a broader perspective, imitation learning is also considered as a strong alternative or bootstrapping method for reinforcement learning. Therefore, we're also curious to see how imitation learning performs in the scenario of quadrotor trajectory planning. And finally, prior learning-based planners, regardless of using reinforcement learning or imitation learning, they are not purely end-to-end. They usually output a set of waypoints or positions and still requires an additional backend for optimizing the trajectory. For example, the Agile Autonomy outputs a set of waypoints and require an external optimization module in order to get a polynomial trajectory. And therefore, in this work, we bridge the gap by having this following contribution. First, we develop and propose an imitation learning framework for quadrotor trajectory planning that is compatible with rules and can effectively learn a novel policy that replicates the behavior of a given expert. And by having the compatibility with rules, we are able to leverage abundant existing quadrotor planning packages, while also extending the existing open source ecosystem of the Kumar Robotics control stack and the AirSim simulation platform. Also, we propose a neural network architecture that is designed for learn-to-end quadrotor trajectory planning that takes the depth image, odometry, and go at the input and directly output the B-spline without needing the additional optimization module for a trajectory. And finally, we develop and provide a complementary simulation environment that assists learning policies with good generalizability. To do so, there are three primary challenges. The first is standard gym-like interface cannot work with ROS as it requires fine control over the exact time step, whereas in ROS, the communication between nodes and among topics will inevitably introduce latency. Therefore, we need to find a workaround, another solution to replace the standard gym-like interface and still be able to control the learning process. Second is training a good learning-based feature extraction for depth image from scratch can be extremely time-consuming. And third is unlike waypoint, B-spline trajectories are extremely susceptible to deviations on node or control points. For example, as shown on the right side of the slide is two B-splines that are generated by the same node vector. There is The only difference between the two B-spline is there is a 1 unit deviation on one axis of one control point, and they generate a totally different trajectory. And therefore, during the training process, we want to encourage the policy to be as close to the demonstration data as possible, while also avoiding overfitting that data set. So move on to methodology. First, I'll give an overview to the proposed imitation learning pipeline. So for the expert in this project, for demonstration purposes, we use the fast planner, which uses a ketodynamic path searching at the front end and using the B-spline trajectory optimization at the back end. It is a local planner. But in practice, when using the framework, you can replace it with any expert planner you want, as long as the package is compatible with Robotics. For learner, it is a neural network-based policy that has two backbone and a planning module. For the process control, since we are no longer be able to use the standard gym-like interface, we instead use POSIX, which is a portable operating system interface, to directly control the learning process at a system level. We use a PID controller from Kumar Robotics control stack in order to execute the B-spline trajectory from the trajectory tracker. We use Unreal Engine 4 to develop the simulation environment. And by using Unreal Engine 4, we are able to develop this simulation environment for both learning and testing. And when each time this environment starts, it's populated with 1,000 random obstacles with random scale, rotation, and location. In this way, it is able to generate both a diverse data set for training well-generalized policy, while also be able to provide a really challenging environment for evaluation and testing of the learned policy. And on the screen is on the slide is a screenshot of the random generating environment in one rollout. However, Unreal Engine 4 and ROS are essentially two completely different and independent software packages with different, fundamentally different representation of the environment. For Unreal Engine 4, it represents the environment by game objects that are actor in an ED frame, whereas in ROS, it represents an environment by point cloud messages that are voxel map in an ENU frame. Therefore, we need to convert the map in UE4 to ROS first. So in order to do that, we first pass through all of the actor objects in UE4 in the ND frame and multiply it with a rotation matrix to convert it from ND frame to ENU frame. And then based on scale property of each actor objects, we calculate their corresponding occupancy cell occupancies on the voxel map. And finally, send the converted map representation to corresponding ROS topics with the message pack RPC. And for controller, it directly takes input from a B-spline tracker that is based on ROS action server. And the output of the controller is MapROS message set based on Marveling protocol and can be received by the AirSim ROS bridge. And then the AirSim ROS bridge executes the control command on the Quadrotor with raw pitch rates and throttle. And the controller is tuned with the Ziegler-Nichols method. And as you can see from the GIF image on the bottom of the slide, the tuned controller can precisely and responsively execute the given control command. And for the network architecture, it takes depth image and a concatenation of odometry and go as input. Then the two different types of information are passed into different backbones for feature extraction. And then the extracted depth image feature embeddings and state feature embedding and then passed into a planning module, which is a 3-layer MLP. And a network architecture and map of hidden units are shown on the slide. So in order to avoid training the feature extractor from scratch, we use the MobileNet v3 with the ImageNet 1K other weight as our own foundation for training the feature extractor. And during the training time, we fine-tune it with backpropagation. And since MobileNet v3 is proposed as a classification network rather than for feature extraction, we add an additional depth post-processing module in order to convert the classification output to corresponding feature embeddings. And in order to kind of have a good balance between overfitting and have a good fit of the demonstration data set, we implemented a learning rate scheduler called the SGDR, which stands for Stochastic Gradient Descent with Warm Restart, which combines cosine annealing with periodic learning rate restarts. So what it does is it essentially gradually decays the learning rate, and when it hits a specific training step threshold, it reset it back to its original value. And for traditional learning rate schedulers, the problem with them is they have the possibility to fall into local minima due to the constantly decaying learning rate. Whereas by using the SGDR, Thanks to its periodic learning restart mechanism, it is able to avoid falling into such local minimum. And as you can see on the rest of the slide, by using that SGDR when comparing to the step error scheduler common with PyTorch, you can see that our implementation of the SGDR is able to outperform the step error scheduler, both in terms of the training loss and validation loss. And also by using SGDR, we're not only able to improve the robustness and generalizability of the learning policy, but we can also reduce the total amount of time we spend on tweaking with the learning rate. So move on to experiments and results. The policies that we use for testing is trained for 425 epochs. And it is trained in the environment that I mentioned in previous slide. And the learn policy is then used for testing in a complex and cluttered environment. And as you can see on the GIF image at the bottom of slides, the learn policy is able to traverse in complex and cluttered environment without collision. And to better visualize and qualitatively analyze the result, we randomly collect 12 B-splines that generated by the learn policy and compare them with corresponding B-splines that generated by the expert planner. And as you can see from the plot on the slide, the learn policy from the B-splines from the learn policy almost perfectly align with the learn policy from the expert planner. And combined with the fact that the learn policy is able to traverse through a complex and cluttered environment, we can show that the learn policy can replicate the expert behavior perfectly. Also, we quantitatively compare the closeness between the learn policy and the expert by using several different metrics, including, as you can see on the bottom of the slide, including MSE loss, cosine similarity, and bilateral distance. And on average, we are able to achieve an MSE loss of 2.03, average cosine similarity of 0.94, and an average bilateral distance of 0.025, which further indicate that our learn policy can perfectly replicate the behavior of the expert planner. And in conclusion, in this work, we propose an imitation learning framework for learning quadrotor trajectory planning by replicating the behavior of a given expert. We also provide a neural network architecture that is designed that can take depth image, odometry, and goal position as input, and directly output a B-spline without needing the additional optimization module. And lastly, we perform the experiments that demonstrates that a combination of the proposed imitation learning framework and neural network architecture can learn from the expert planner effectively. And for future work, the first and foremost things we want to do is definitely do sim-to-real transfer, since ultimately we want the learn policy to be able to perform inference on a physical quadrotor. The second is we want to add another backbone for predicting future embeddings with latent diffusion model, as recent works that I read using latent diffusion model to predict future embedding in order to speed up the video processing time, which since the nature of video processing and quadrotor trajectory planning are all sequential decision-making tasks, I think the similar idea should be able to transfer to quadrotor trajectory planning as well. And the third is, speaking of the sequential decision task, we want to replace the MLP planning module with RNL transformer, since this model architecture is specifically designed for doing sequential tasks. And fourth, we want to use this proposed imitation learning framework to learn from a costly expert, such as a jointly optimized perception aware planner, which being one of our core motivation that we want to use this framework to kind of reduce computational costs with costly traditional planner. Lastly, although an end-to-end policy has the best efficiency, the problem with it is lack of the interpretability and expandability. And another direction would be only replacing the part that is computationally expensive in traditional planner. And we already identified one that is a safety corridor generation process. And another direction is using the proposed imitation learning framework to only learn a policy that for safety corridor generation and see if this can help when using this in a traditional optimization-based planner. And finally, in the end, I would like to thank Professor Vijay Kumar for his support on this project. And I would also like to thank Yue for her insightful suggestion on the research direction and diligent help with the development. And finally, I would like to thank the robot department for providing solid course and research opportunity to help me build up the foundation that I need for this project. And that is the end of my presentation. Thank you for listening. I'm happy to answer any questions. Uh-huh. I think first and foremost is in simulations, the depth image that we get is really ideal. And whereas in real world environment, you can see that there is a lot of glitches on the depth image. So I think there should be a extra like cautious on the depth image part. But I haven't figured out how to kind of bridge this gap, like how to simulate the kind of the noise, like more realistic noise in a real world scenario to get it kind of like a transfer learning to transfer the learn policy in simulation environment to real world environment. But I think ultimately I'll find like maybe a noise pattern that can be used in this scenario. Uh, mm-hmm, mm-hmm. Yeah, actually the environment is random generated. Like each time when it starts, it's generate a totally different complex structure. And the reason for doing that is because our idea of using this imitation learning framework is to transfer high cost traditional planners to a low cost learning based planner. And a problem with learning based approach is always tend to overfitting the data. And by having a really diverse demonstration data that have really different input and output set, we are able to make the learning policy as generalized as possible. So that is the reason why I kind of want to have a really diverse and complex cluster environment.